Hello, everyone, and welcome to the second in a series of videos on related rates. If you've watched my first video, you know that in that video I gave you an overview of the general process, and now I'd like to try and give you a little more complicated example of how to solve a related rates problem using the techniques that I developed in that first video. So let me share my screen at this time and put the problem up for us. Here's how the problem reads. How fast is the shadow on level ground cast by a pole that is 50 feet tall, lengthening when the angle of elevation of the sun is 60 degrees and is decreasing by 1/4 radian per hour? Okay, we've got a lot going on. That's one sentence, believe it or not. And we've got a lot going on there. So if you'll recall that when we do related rates, the first thing that I try to do is either draw a picture or come up with some variable definitions. I'm going to draw a picture of a little bit of what's going on here. So we have some level ground. So let's look at that. We have some level ground. I'm going to get my line drawing tool here. We have level ground. I'm going to represent that by this red line right here. Now, the shadow is going to be lengthening along this level ground. We also have a pole that is standing there. We have a pole standing on the ground. There's my pole right there. Let's try and make it straight because it's not straight. So let me go back to that. Let me get rid of this pole here. There we go. Try again. So I'm going to draw a line here. There's my pole on level ground right there. So that's 50 feet. Now, this height of this pole, regardless of what's going on with the shadow, is fixed. So anything that's fixed, I'm going to go ahead and put in my drawing. So I'm going to say that this height is 50 feet. Whoops. 50 feet. Okay. I don't tend to put anything in my drawing at this point that's not fixed. I'll write them as variables, but I don't put anything in there that's not fixed. The length of this shadow is not fixed. It's going to get longer as the sun goes down. So I have another segment here on this problem, which is I've got the top of the pole and I've got the sun. So something like this. Let me come back out and fix that. So I've got something like this, where the sun is casting a shadow because it's hitting the pole, right? So something like this, okay? And the sun is up here, of course, right? So let me draw my sun. I'm just going to represent that by a yellow dot right here. This is going to be my sun, right? And so the sun, now the other thing I need is I need a line. So I'm going to draw another. I'll show you why I need this in a minute. If you're not sure, don't worry about it. But I'm going to draw a line here. Something like this. Okay, there's my sun. So, okay, now that's kind of the picture, and I've got an angle down here that my angle is making. I should say that the sun is making. So I have an angle right here, and I'm going to draw that in black. I'm going to draw this in black. So I have an angle here that my sun is making, and I'm going to call it theta. You can call it whatever you want. I'm going to call this length x, okay? This is the length of my shadow that the pole has along the ground. So what's happening, it says, how fast, remember how fast is one of our keywords for, I'll write it in green. How fast is one of my keywords for derivative. How fast is the shadow on level ground cast by a pole that is 50 feet tall, lengthening when the angle of elevation of the sun is 60 degrees and is decreasing by 1/4 radian per hour. All right, so we've got some things going on here. Let's do what we always do, and let's get some variables for my statements here. I'm gonna get some, how fast is the shadow on level ground? So I need a variable for the length of my shadow. So the first thing I'm gonna do is I'm gonna say oops. Let x, oops, be the length of my shadow in feet, okay? X is the length of my shadow in feet. Okay, I also have theta. So let me put theta on the board here. Theta, which is just a Greek letter from the Greek alphabet, but we use it to represent angles. So I'm going to say let theta equal the measure of the angle of elevation of the sun Now you say, well, but I thought it was 60 degrees. It's 60 degrees at the moment we're talking about, but this angle changes with time, so it's variable. The height of the pole doesn't change. The length of the shadow and the size of the angle are changing. Okay, So I've got two variables once again, and correspondingly, I have two rates of change. So I know that dx dt is going to represent the rate of change of the length of the shadow with respect to time. And similarly, I know that d theta dt, which I'm going to write in marker over here, d theta dt is going to equal the rate of change of the angle of elevation of the sun with respect to time. So what I've done here now is I've set up my picture. I've set up my variables and my rates of change, okay? What I need to do here, unlike the first example where it was just a formula, here we have to understand a few things, okay? How fast is the shadow on level ground cast by a pole that is 50 feet tall? Lengthening. So this, we want to find this piece here. How fast is what? How fast is my shadow lengthening? This means that this will be positive because it's getting longer. This is positive derivative, right? We know it's a derivative from up there. When the angle of elevation of the sun is 60 degrees and is decreasing, so here's my the angle of elevation of the sun is decreasing by 1/4 radian per hour. Okay, so here I've got the shadow length is getting longer as the angle diminishes, as it gets smaller, as the sun goes down, gets closer to the horizon, this angle gets smaller, okay? The reason I drew this yellow line up here is to remind you about angles of elevation, which is what this is. Angles of elevation are below your horizontal frame of reference. Here, it's where the sun is. So the sun's up here by this yellow dot. Angles of elevation are below that field of vision from the ground. Angles of depression would be, or declination would be from this point of reference over here, which would be down below the horizon, okay? Or down below, I should say not the horizon in this case, but the horizontal, okay? So we're looking at this angle here of elevation. That's a throwback to trig or pre-calc, depending on when you saw that. Now, we need to come up with a relationship, okay? This is a right triangle because we assume that the pole is straight in the ground is level, all that good stuff. So we assume that we're at a right angle to the ground. Pretty safe assumption, but got my angle there. Now, your first thought might be Pythagorean theorem, but I don't have this length. I don't have the length that the sun is making with the ground. I don't know that. But I do have this relationship theta. So what I'm going to do here, you have a couple of choices, but I only have two sides that are known. I have 50 and I have x. Now, could I get the third one by the Pythagorean theorem? Yes, but it's also unknown in terms of x. So I would probably stick with using just what's here. And that leaves me with opposite side to the angle over the adjacent x. Opposite over adjacent, or x over 50, for example, which would be cotangent. I'm going to use the tangent relationship here and write my equation. So I'm going to write my equation next. And so we have tangent of theta, and I'm going to write my angle here. Tangent theta. Remember, tangent theta from trigonometry is equal to opposite over adjacent. So I have, this is 50 over x. Now, this is not a hard equation to solve. This relation, this was an example of how to get a relationship when you don't have it, okay? But there are a couple of more tricks in employing the related rates in this problem. So I'll show you that right here. But here's our equation. Remember that the next thing we do, we've drawn the picture, we've stated the variables, we've gotten the equation. The next thing we have to do is differentiate implicitly. Let's do that on the next whiteboard here. So we have the following. Tangent theta. Tangent theta equals 50 over x. Now, remember what we said before about differentiating every variable with respect to time. So we're going to have to differentiate theta and x. Before I do that, though, I'm going to do a little algebra manipulation on my equation. Tangent theta. So this is going to be tangent theta. And I'm going to rewrite the right-hand side as x to the -1 power. Because remember, x in the denominator is like 50x is negative 1. Now, what that's going to allow me to do is I'm going to differentiate both sides of this with respect to time. Remember that the derivative of tangent is secant squared. So this is secant squared theta. Secant squared theta squared theta is equal to the derivative of this. So this is secant squared theta, and I need my d theta dt, right? Secant squared theta d theta dt. Okay, so there's my secant squared theta d theta dt, and that's going to equal my derivative here. So remember, negative 1 comes down, so I get negative 1 times 50, that's negative 50 x, and remember, I take 1 off, so negative 1 minus 1 more is negative 2, so negative 50x to the negative 2 power and dx dt. Dx dt. Okay, there's my equation. Secant squared theta d theta dt is negative 50x to the negative 2 dx dt. Now, if you look back at the problem that we were doing, we know what some of these are. It says the angle of elevation of the sun is 60 degrees. So we know what theta is. And decreasing by 1/4 radian an hour. So essentially what happens here is that they gave me, and we'll come over for this in a minute, what they've given me here. Let me take a timeout. So what we know from the problem is that my theta is 60 degrees. Now, theta is 60 degrees. We're going to come back to that in a minute. 60 degrees. And we know that my d theta dt, d theta dt is decreasing at negative 1/4 radian per hour. So now I have d theta dt, right? And what I have here is that I'm looking for this rate of change. I know what this is. It's decreasing because remember, the angle this is. Negative 1/4 radian per hour. Okay. Now, the one thing to be aware of, notice, this is why I advocate degrees. Theta is 60 degrees, d theta dt is in radians per hour. So you need to be able to convert this. So that's the first little tricky establishment about this. Okay, you have to have consistent units. So the first pitfall is that 60 degrees is going to equal pi over 3 radians. Now, how did I get that? Well, I know that so I have, if I want to convert it, it's 60 degrees over 1 times I want degrees to cancel. So I'm going to put pi radians up here, and I'm going to write the word. It's not necessary, but I want to keep the units straight. So this is 180 degrees, because in case you've forgotten, pi radians is 180 degrees. A full circle is approximately 6.28 radians. And as we can see here, 60 goes into 183 times. So if I do the cancellation, this is going to give me pi over 3 radians. So that's the first pitfall in here, okay? You have to convert that so that the units will work. Pi over 3 radians. Now, I have theta. I don't have x. Notice my equation has an x. How am I supposed to get that x? Well, if you remember, we know this is 50. We know theta at this point is 60 degrees. So I can find that x using another skill from geometry and or trig, and that is I can use similar triangles. There are other ways of doing it too, but trigonometry or special triangles, or even not necessarily similar, I think I said similar, special triangles would help you the most. So if I go here to another whiteboard right here, because this is the main one that I'm working on, and I say, all right, recall that we have a triangle. Okay. So there's my triangle. And there's the ground and there's the sun and whatnot. So now I know this angle. So there's my angle. There's my theta. And if this is 60 degrees, then remember the angles in a triangle have to add up to 180. So that must mean that this is 30 because again, all right angles are 90 degrees. And we established previously that this is 90. So we have this situation here. Now you might say, how does that help me? Here's my angle, right? You might say, well, how does that help me? Well, now we know that this height is 50, and we're going to use that to our advantage. We don't know what this x is at this point. So, but I do know that the side opposite the 30 is the shortest, and the hypotenuse is twice as long as the shortest. So here we're going to call on some, this is prerequisite geometry or trig knowledge. I don't care where you learned it. I just care that you learned it, okay? This is x here at the bottom. So the side opposite, the 90-degree angle is always the longest. So it's 2x. Now from here, I can solve for the x, and I need to do that. So I'm going to write my equation x squared plus 50 squared. Now be careful here. You're squaring the entire 2x. So if you want to write this properly, you're going to write 2x quantity squared here. 2x squared. So this becomes x squared plus 50 squared is 50 times 50. That's 2,500. So I'm going to go ahead and put that in now. Plus, and this is 4x squared on this side. So I'm going to solve for x. So I have 4x squared. Now, I'm going to do some manipulations here. And I'm going to move this x squared over. So I'm going to have 2,500 is equal to 3x squared. So from there, what I'm going to do is I'm going to divide by 3 and take the square root. So I'm going to assume that since you guys are calculus or soon to be aspiring, you'll be able to do this. This is 2,500 over 3. So 2,500 over 3 is equal to x squared. Now, This is x. And what I want to do is, as I mentioned, take the square root of both sides of my equation. So I've got x, I'm going to put it up here. I've got 50 over the square root of 3 50 over the square root of 3 is equal to x. So now I'm going to leave it that way because you're going to see that we're going to do something with that. But that's my x at the instant when the sun, the angle of elevation is 60 degrees, okay? We're going to leave it like that. That's our prerequisite knowledge. Now, if we go back to our equation here, so now I've got some new, so remember I'm pulling from this equation here, secant squared theta d theta dt is negative 50x to the negative 2 dx dt. So it's going to get larger, okay? So what do I have to do? Well, I'm looking for so what I have now is I have some extra knowns. I know what theta is. I know what d theta dt is. I know what x is. And I want to find what dx dt is. So we have the following. We have secant squared, secant squared theta secant squared theta d theta dt. I just want to put this on the theta. Oops, I don't want to do that. I want to make this secant squared theta d theta dt. And remember, you're going to need trig knowledge for the secant squared. Is equal to negative 50x to the negative 2 dx dt. So in this case, I'm just going to plug everything in now and solve it. Let's take a look at, we made some changes. We we converted some stuff, so let's take a look. We know that theta is 60 degrees. It's also pi over 3 radians. In this case, I'm going to go with pi over 3 is my theta. That's 60 degrees. Now, why did I convert that? Because my d theta dt, if you'll remember, let's go back. My d theta dt was 1/4 radian per hour, and it's decreasing. So this means that when I do it, I know theta is 60 degrees. I know that d theta dt is a negative 1/4. So this is going to be d theta dt is 1/4 radian per hour, decreasing. So we have negative. This is negative. One quarter. Yes, you can make that a decimal if you choose. I usually just leave it intact. But this is radians. Now, it's negative, notice. So that leaves me, I know what theta is. I know what x is. So let's plug it in. So we're going to have the following. Secant squared pi thirds and then times d theta dt, which we know is negative 1/4, is equal to negative 50 x. Remember, we got on the other whiteboard, x was x was this thing here, 50 over the square root of 3 for the angle that we talked about. So we have now what is, and I'm going to write that in a note here, x equals 50 over 50 over the square root of 3. If you plug everything in there, we're going to get our answer. So it's just going to take some some plugging, but it's not anything that you don't know how to do already. At least I hope not. It might be a little bit awkward, but I don't think it'll be something that you don't know how to do. This is 50 over the square root of 3, the value that we got from the special right triangle. So there's all the stuff you need. So let's put it in. So we have now pi thirds is 60 degrees. Secant is 1 over cosine. Cosine of 60 is a half. So 1/2 squared is 1/4. Okay, secant squared of that. So remember that was cosine squared. Once again, pi thirds. Cosine is a half. Square it, you get a fourth. Flip it over, you get 4. So secant squared of pi thirds is 4. Okay, that's 4 times a negative 1/4. And I forgot some parts to the equation here. This is over. So this is x squared. So now x, remember, was the rate at which the shadow was changing, which is 50 over the square root of 3, right? So this is 50 over so this is 50. X, remember, is 50 over the square root of 3, and I'm squaring it. So I'm back to this answer at this one that I had previously. So now where? So you can work that out. And that is going to be, this is dx dt. Dx dt. So just to clean this up just a bit, we're solving for dx dt. So we have 4 times negative 1/4 is equal to negative 50 over 50 square root of 3 squared dx dt. So let me go one more whiteboard here for us just to finish this problem. And I'm going to say that we have 4 times a negative 1/4 is equal to this negative 50 on the top. And remember, the bottom of this is going to be, I'll make it a little larger. The bottom of this is going to be $50 over the square root of 3. And I'm squaring it. Dx dt. So now I have, this is dx dt. So I have 4 times negative 1/4. This is negative 1 is equal to negative 50. Now I'm going to try and clean up the bottom. 50 times itself is 2,500. So I have 2,500 over 3. So this answer here is 2,500 over 3. And that's equal to dx dt. So now I'm going to solve this. So this is going to be I'm going to say that this is this complex fraction. It's going to be negative 1 is equal to, I'm going to flip the fraction. So negative 50 times 3, this is negative 150 over 2,500 dx dt. Oh, this is my fraction bar right here. And so then I'm going to say that this shadow, I'm solving for dx dt, remember. So now I'm going to multiply by that negative. And if I take, let me do me share the calculator for a minute. I have, hold on, 2,500 over 150. Let me bring up the calculator for us. And share the screen. So I have 150 over 2,500. And this becomes 0.06 or 600ths. So what I have here is if I go back to this piece here becomes a negative 0.06. So I have, essentially I'm dividing by this. So now I have dx dt, and I'm gonna flip my sides around. Dx dt equals this, remember, is -1. This is um, 3/50. So this is 0.06, and it's negative 0.06 dx dt. And I'm going to divide by 0.06 negative. So if I do that here, I have 1 divided by 0.06. That comes out to 16.67. Or if I want to convert so I have 16.67. So this is going to be dx dt then is going to be, is going to be dx dt, as we've seen. And remember, we had 2 negatives. So we end up with a positive answer. Dx dt is approximately 16.67. And that's actually 16 2/3, if you want to do that. 16.67. So it's going to be in feet. per hour. So the shadow is getting longer by 16.67 feet per hour. I know that was long. I know that was a lot of arithmetic, a lot of prerequisite trig knowledge, but that is it for this video. I hope that you learned something. I hope that it was helpful to you, and I will see you in my next video. Thank you so much.